Hey everyone, we're looking at section 6.1 today, and of course this is the beginning of chapter 6 where we are going to be talking about normal distribution. Now I'll tell you right up front that it will be a lot better if you go ahead and read this chapter, and of course right now read this section because there's a lot of information here that will be more beneficial to you if you try to read this on your own than me just reading the handout out to you, okay? So I would say go ahead and read this section if you haven't already, and you will get a lot of good information from here because I will not be reading each and every part of this handout. So it will be better for you to read it, and I will just highlight the things that I think are important, but there could be, of course, other things that you should know about this, okay? So in the last chapter, we had talked about discrete variables and the distributions for those discrete variables. Now in this chapter, we will be talking about continuous variables. So remember, continuous variables can assume all values between any two given values, right? So if you think of examples for continuous variables, you can think of the height of adult male, you can think of body temperatures of rats in this case, cholesterol level for adults. So all of these, you can basically think of them as being continuous variables because you can have the height of 5 feet or 6 feet, but you can also have somebody who's 5 feet 3 inches and maybe a little bit extra on top of that, right? And they could have any value in between, like 5 feet 3 inches and 5 feet 4 inches, right? They could be somewhere in the middle of those two values. So that's why these are considered as continuous variables. Now basically when we're talking about continuous variables and their distributions, we are saying many continuous variables have distributions that are bell-shaped, and for these type of distributions we say for the variables we say that they are approximately normally distributed variables. So this example here is talking about it. If there's a researcher and they select a random sample of 100 women, and basically we're measuring their heights, let's say, and construct a histogram based on that, then basically the histogram that you draw will come out looking like this first one over here. Okay, so we took a sample of 100 women, we measured their height and constructed a histogram based on that. Now, if we increase our sample size, so maybe instead of 100 women, we go up to, let's say, 1,000 women, or maybe even more, and then decrease the width of all our classes. So instead of having the width like we do in figure A, we narrow that width down, then basically our histogram could end up looking like one of the figures B or C. So depending on what your sample size is and what you decide the width of your classes should be, you could get a histogram which looks like figure B over here or figure C over here. Now for this last figure, we're saying if it were possible to measure exactly the height of all adult females in the United States and plot them, then your histogram would actually start looking more like this normal distribution curve that we have here in figure D. Because what would happen is all those histogram bars that you're seeing, let's say in figure C over here, if you take all those histogram bars and you make them really, really narrow, because your sample size is now going to be all the adult females in the United States, it would actually form this smooth curve, which is what we're calling as the normal distribution curve. So of course we also call it as the bell curve for the obvious reason, because that shape looks like a bell shape. Or it's also named after the German mathematician who derived this equation, and so sometimes it's also called the Gaussian distribution curve, and of course that's named after Carl Friedrich Gauss over here, okay? Now basically, this is a theoretical curve, this is a theoretical distribution, so no variable is going to fit this exactly, but of course we can still use this idea of a normal distribution to help us describe a lot of these variables, and you can kind of read some of that in here. So we'll be talking about the properties of normal distribution, we'll look at different applications, and we are also going to talk about the central limit theorem, I think either in the next section or the one after that. And then we will also talk about how you can use a normal distribution curve to approximate some of the other distributions, like the binomial distribution, which we talked about in chapter 5. Okay, so let's get into our discussion for normal distribution. So we're saying in mathematics, curves can be represented by equations. So if you think about the equation of a circle, which is right here, x squared plus y squared equals r squared, where r, of course, is the radius of your circle. So we're basically saying you can use this concept of a circle, which can represent, a wheel or a gear. They are circular in shape, but that does not mean that, you are getting a perfect round when you're manufacturing these gears or these wheels. But the idea is we can still use the equation and properties of the circle to study the aspects of, let's say, our wheel. So you could study its area, the velocity, or even the acceleration by using this concept of thinking of it as a circle. So in that same way, we know that the normal distribution curve is a theoretical curve, but we can still use it to study variables that may not be perfectly normally distributed, but they could be approximately normal, and so we can still use this concept of a normal distribution with them. Okay, so just as your definition, we're saying if a random variable has a probability distribution whose graph is continuous, bell-shaped, and symmetric, we would call it a normal distribution, and the graph would be called a normal distribution curve. Now this one here is your equation for the normal distribution. So here you can see we have y equals e raised to the power of negative parentheses x minus mu quantity squared divided by 2 times sigma squared, and then that whole thing is divided by sigma times the square root of 2 pi. So of course e is the natural number e, which is approximately equal to 2.718. Of course pi is our approximation 3.14, and then mu would represent the population mean, and sigma would represent the standard deviation for the population again. But of course we're not going to be using this equation when we are talking about normal distribution, because normally in applied statistics we either use the tables or we use technology like calculators or a computer program to help us solve these. So you don't really need to know the equation, but just remember that the normal distribution does have an equation behind it, okay, which is where our tables and everything else came from. Now the one thing you have to remember about when we are working with this normal distribution in applied statistics, that we are mainly interested in the area that is going to be under this normal distribution curve. So we're not so much interested with what the y value is going to be when we graph these normal distribution curves. We're more interested in what area is going to be underneath that curve, okay? And so a lot of times when we draw our normal distributions curves, you will see that we don't really draw the y-axis. Normally we just leave the y-axis out, okay? All right, so the two things that we need to draw our normal distribution curve is actually going to be the mean and the standard deviation, which will help you with the shape and the position of the normal distribution curve, okay? So we are saying each normally distributed variable has its own normal distribution curve, which will depend on the values of the variable's mean and standard deviation. So each variable, each continuous variable, which is normally distributed, will have its own normal distribution curve, and it will depend on that variable's mean and standard deviation. Okay, so something to remember, that each variable will have its own curve to go with it. Okay, now I just want to talk about the comparison here between what happens when you have different means and same standard deviation, and if you have the same mean with different standard deviation. So they're saying, let's say we have one normally distributed variable that has mu at 0 and has a standard deviation of 1, and there's another normally distributed variable that also has the mean at 0 but has a standard deviation of 2. So that's going to be shown here in our first graph, part A. So you can see both my curves have the same mean, right? Because this is our mu right at the center of our curve. But you will see The one that kind of looks like a brown color is going to be where our mean is 0 and standard deviation is 1, so it's a little bit more steeper, right? And then the curve that you have, which is kind of in this light blue, has the same mean of 0 but a standard deviation of 2. So it looks like that curve in the blue spreads out. So the larger your standard deviation is going to be, the more your curve for your normal distribution is going to spread out. Okay, so standard deviation increases, the shape of the curve spreads out. Now, let's say we have one normally distributed variable that has mean at 0 and standard deviation at 2, but another normally distributed variable actually has the mean at 2 and standard deviation also at 2. So in this case, you will notice that my mean is different, but they both have the same standard deviation. So what happens in this case is then the shape of your normal distribution curve is actually going to stay the same, but the position changes. So this variable that had the mean at 0 is going to be right here, and the second variable that had a mu at 2 has basically now moved 2 units to the right. So in this case, you can see when our standard deviation stays the same, but the mean changes, then the position of our curve is going to change. Whereas in this first example over here, where our mean was the same, but the standard deviation changed, that means the position of the curve is going to stay in the same place, but the shape of your curve is going to change, right? Because this one spreads out more. So just to show you the comparison between the two types of changes that you can kind of see in your curve, so the shape and the position. So just as a summary for our properties for the theoretical normal distribution, of course your curve for the normal distribution has to be bell-shaped. Your mean, median, and mode are actually all going to be equal, and they are going to be at the center of your distribution. So right in the middle of your distribution is where you'll find your mean, median, and mode. And of course your curve is going to be unimodal because you only have one mode, right? And that's going to be that little peak at the center of our curve. Now this is going to be an important thing. You have to remember that your curve is going to be symmetric about the mean, which means if you think of that mean being in the center of your curve, then you have, if you were to fold your curve along that line, which would be your mean, then the two halves of your curve are going to be exactly equal to each other, right? They're going to be equivalent. Your curve is going to be continuous, so there should be no gaps or holes in your curve. You should have a nice continuous smooth curve. And what that basically means is that for each value of x, you have a corresponding value of y. Okay? Now here's another thing to remember. Your curve will never touch the x-axis. Okay? You will always see that it's a little gap between the x-axis and your curve. So we're saying theoretically it does not matter how far in either direction the curve extends. Just remember that it never meets the x-axis. It gets really close to it. It just never touches it. Okay? And next thing that is going to be crucial is that your total area under the curve is going to be equal to 1 if you're writing it as a decimal, or as a percent would be 100%. So basically 100% of your data is going to fall underneath this normal distribution curve. Okay? And then of course the other part which we had talked about when we had looked at empirical rule back in chapter 3, you should know that within one standard deviation, and this is talking in terms of area under your curve, within one standard deviation of the mean, you're going to have approximately 0.68 or 68% of your data. Within two means from your mean, you're going to have 0.95 or 95% of the data. And within three standard deviations, we will have 0.997 or approximately 99.7% of our data. Okay? So right here, you can see in the center we have our mean, which will also be where you have your median and your mode. Now, on the right-hand side of your mean, in all of this area, so starting from the mean all the way to the tail, you will have 50% on the right-hand side, and same thing on the left-hand side from the mean all the way to the tail on the left, you will also have 50% of your data. Now within one standard deviation, we have 68%, so that's within one standard deviation. Okay, within, so that's the about 68%. Within two standard deviations, we are looking at 95%, so that's going to be all the way from here to here. This will make up 95% of the data values. And then of course within three standard deviations, above and below the mean, so from here all the way here, this will be about 99.7. So that means this little bit of the tail area that we have left over is going to be the remaining. Together both of those sides will end up making 0.3% of your data in just those remaining tail areas, because remember, the total area underneath our curve will add up to 100%, and since this guy only goes to 99.7%, that of course tells you you still have 0.3% left over in those tails. Okay, so yeah, that was section 3.2, where we talked about the empirical rule. So that's the same thing that we are doing here. Empirical rule is, if you remember, also called the normal rule, and that's coming from this normal distribution over here. Okay, alrighty. Now they are also saying, recall that from chapter 2, the graphs of many distributions can have many shapes. Now if your data values are evenly distributed about your mean, then we say the distribution is a symmetric distribution, right? And that means if you're talking about symmetry, we're also talking about the normal distribution here. So this over here, this figure on the top in the blue is talking about the normal distribution, where your mean, median, mode are all going to be at the center of your data set. Okay, now they're saying when the majority of your data values fall to the left or to the right of the mean, we say our data or our distribution is skewed, right? So if the majority of your data values fall to the right, then we fall to the right of the mean, then we're saying it's a negatively or left skewed distribution, which would look like this. So you can see our mean is going to be to the left, median is going to be in the middle, and then mode is going to be to the right of both of them. If of course majority of your data value falls to the left of the mean, then we say it's a positive or a right skewed distribution, so it would look like this. So in this case, your mode is going to be to the left, median is going to be in the middle, and then mean is going to be to the right. Okay, so you can kind of see what that skewed distribution looks like, and of course in the middle we have our normal or symmetric distribution, right? And they're telling us that the tail of the curve indicates the direction of your skewness. So if your tail is on the right, we say it's right skewed or positively skewed. If your tail is on the left, we say it's left skewed or negatively skewed, right? Alrighty. Now let's look at normal, a standard normal distribution. So since we know that each normally distributed variable can have its own shape and position of the curve, right? Because each normally distributed variable would have its own curve based on its own mean and standard deviation. If we wanted to try and standardize that so that we could apply it to many different applications, they are saying in practical applications, you want to have a table of areas under the curve for each variable. So what that means is if we could use a standard normal distribution, then we could take all variables which are normally distributed, convert it to the standard normal distribution, and then we could apply this table of areas for our curve, and we wouldn't have to recreate it for each variable. So basically they are saying to simplify this situation, the statisticians basically came up with this idea of a standard normal distribution. And what that means, you're still looking at a normal distribution, but your mean will always be at 0, and you will have a standard deviation of 1. And so here you can see our mean is at 0 when you are going from one standard deviation below. to 1 standard deviation above, you will have approximately 68% of your data within that 1 standard deviation. Within 2 standard deviations from the mean, we would fall into a total of 95% of our data. And again, within 3 standard deviations from our mean, we would fall within 99.7% of our data. Now you will see these guys are actually going a little further on that approximation. So they are trying to go a little bit further out than what we will be, but still our answers will come out to be pretty close. And then remember, we have just a little bit of our data left here in the tail, and since they are going to further approximation, this is only showing up as 0.26%, but we just think of it as being 0.3%, which is left off in the tails. Okay, alrighty. Now basically the idea is the values under the curve can also think about it as being the proportion of the area. So if they are saying, for example, the area between the mean and your 1 standard deviation above or below the mean is going to be 0.3413, or approximately 34.13%. So you can also think of that as the value under the area is giving you the proportion of the area in each section. Now, when we're talking about the standard normal distribution, your equation changes a little bit from what you had seen here with this, because this was just your general normal distribution equation over here. But when you're talking about the standard normal distribution, then that equation changes a little bit. We're still not going to be using the equation to do our calculations, but you should be again kind of aware of how your equation changes. And you will notice we're actually using the z variable over here. And this z variable, if you remembered, we had also talked about this formula in section 3.3 where we called it the standard score formula, and it's basically going to be this one right over here. So z-score is the formula is the value that we're looking at minus the mean for that variable divided by the standard deviation, and of course you can look at it as x being our data value minus mu divided by sigma. Okay, so again you can go back and reference your handout for section 3.2 and 3.3 to kind of look at some of these calculations and rules that we had talked about. Okay, so again we had talked about the area under the normal distribution is used to solve practical application problems, and we can talk about if we were trying to find the percentage of adult women whose height is going to be between 5 feet 4 inches and 5 feet 7 inches. So if you wanted to know what percentage of women will have a height between these two values, we could use the normal distribution curve for that. If you wanted to find what's the probability that a new battery will last longer than 4 years, again this is where we would bring in this idea of normal distribution curve, right? So they are saying once the x values are transformed from just being the x values for that variable into our z values, then you can actually use the standard normal distribution table to kind of come up with that area or that probability for these values that we are looking at. So they're saying the z-score or the z value is actually the number of standard deviations that this particular x value is going to be away from the mean. And remember, if your z value is positive, that means the number is above the mean. If the z value is negative, the number is below the mean. So they're telling you you can look at table E in appendix A to see what that normal distribution table looks like. It will give you the area up to 4 decimal places under your curve, and you will see your z values go from negative 3.49 to positive 3.49. So let me show you what this table will look like. So you will see we actually start with the negative side of our table, and we're going from negative 3.4, which your z-score is broken up into the rows and columns. So 0, negative 3.4 is here, and then the second decimal place is actually here. So if you're looking at negative 3.49 as your z-score, you use negative 3.4 from here, and then for that last 9 at the end, you have to go over here to the last column. So this is kind of how the normal distribution table works. But anyway, so you can see this is the negative side of the table, and then this is going to be the positive side of your table, which will also go to positive 3.49. So there's 3.4 over here, and then again for the last 0.09 you have to go on the other side. Okay, but we'll talk about this table a little bit more. So how do you find the area in your standard normal distribution curve? Okay, so they are saying for the solution of the problems using this distribution is going to be a two-step process. And basically the first step, of course, is going to be draw your curve and then shade the area for which you are trying to find the area for. And then they are saying find the approximate figure looking at this procedure table over here. And then based on those directions, we will have to use our calculations to come up with that. Okay, so the idea is if they ask you for a value which is going to be to the left of any of our z-score or z-value, what we will have to do is go to our table, look up the z-value, and use the given area. So whatever the table gives you the z-value is going to be the area of the shaded portion over here. So this part, or this part, depending on is your z-value above the mean or below the mean. Okay? If they ask you for the area which is going to be to the right of the z-value, so again, depending on do you have a positive or a negative z-value. So if you are trying to find this area, since by default your normal distribution table always gives you the value to the left of the z-value, which is what we're seeing in case 1. So if you wanted to find the z-value, the area to the right of the z-value, you actually have to look up the z-value, what that area is going to be, and then subtract that answer from 1. Why 1? Because remember, your entire normal distribution curve is 100%, right? Which is 1 as a decimal number. So if you're trying to find the area of the shaded portion, which is going to be to the right of your z-score, you have to subtract it from 1. If you are trying to find the area between two z-values, you basically find the area value from the table, and then you basically end up subtracting those two areas. And of course, you will always subtract the smaller number from the larger one, because area cannot be a negative value. Okay, so let's say how we can use our table to find these values for our z-scores and come up with that area. So they're telling you the table gives the area under the normal distribution curve to the left of any z-value given in two decimal places. So by default, the normal distribution table will always give you the area which is going to be to the left of the z-value. Okay, so they're saying, for example, if you wanted to find the area which is going to be to the left of the z-value of 1.39, you're going to go to the left column and find the number 1.3, and then go to the top row and find 0.09, so that you can find out what the z-score corresponding area for the z-score of 1.39 is going to be. So basically, first of all, we need to go to the positive table. We need to find 1.3 over here, and then we need to find 0.9 in that row, and then where the two will meet is going to be the area for our z-score. So at 1.39, the total area is going to be 0.9177, and you will see that's kind of what they're illustrating here in this little figure over here, 0.9177. So we're basically saying, if this is our normal distribution curve, let's say, okay, and then in the middle, of course, be what our mean is going to be. So if you are at 1.39 as your z-score, then we are basically saying this area which is going to be below or to the left of 1.39, this whole area is going to be approximately 91.77%. So we are saying 91.77% of our data values are falling in there, but you can also think of it as being probability. The probability of our data value falling in that region or in that area is also going to be 91.77%. So this not only works as area under the curve, but it actually also works as probability for that particular data value or for that particular z-score. Okay? So before we get into probabilities, let's talk about just being comfortable with doing these three different types of calculations with our normal distribution table over here. Okay? So they are saying find the area under the standard normal distribution curve to the left of the z-score of 1.73. So that means you're looking at 1.7 on your leftmost column, and then on the top row you are going to be looking at 0.03. Okay, so 1.7 will be right here, and then 0.03 is right here. So it looks like they are meeting at this number, which is 0.9582, and you will see that's what we end up getting, 0.9582, which is going to be approximately 95.82%. So we're saying 95.82% of the area is to the left of the z-score. So the shaded area right here is going to be 95.82%. Okay, so remember, by default, all of these values that you're seeing here are all going to give you that value which is going to be to the left of your z-score. Now, if we wanted to find the area which was going to be to the right of the z-score of negative 1.24, which means again we're looking at negative 1.2 in our leftmost column, and then on the top row we will be looking at 0.04. So let's go to our negative table, and that's going to be negative 1.2, and that was 0.04. So negative 1.2 and 0.04 is right here. So let's see, as we go down, it looks like we are going to be at 0.1075, and you can kind of verify that here. So negative 1.2, 0.04, both of those are meeting at 0.1075. So you will see that's what we can end up getting, 0.1075. But since we are talking about the area, this 0.105 is actually talking about this portion right here. So this part is 0.1075, or you can think of that as being 10.75%, but we're interested in the area to the right of it, and that's why we need to subtract it from 1. So you're going to do 1 minus the 0.1075 to get this answer of 0.8925, or basically we're saying 89.25% of the area is going to be to the right of your z-score. Okay, so anytime you are looking at the area which is going to be to the right of your z-score, remember you need to subtract it from 1. So they're saying in this situation, we subtract the area of 0.1075 from 1, since the table would only give you the area of up to negative 1.24, which means they're talking about just showing you the area to the left. Okay, so to get the area on the other side, of course, you would need to subtract it from 1. Now, the last case we want to talk about is what if they were asking us to find the area which was going to be between two z-scores. So here you've got 1.62, so that's going to be 1.6 plus 0.02, and the other z-score is negative 1.35, so that's negative 1.3 plus 0.05. So let's do the positive one First, we've got 1.6 and then 0.02. So 1.6 is here, 0.02 is here. So if you see where these two guys will meet, looks like that's going to be at 0.9474 for that first one. So you should be able to verify that here. That's 0.9474. Now let's look for the other one, negative 1.3 and 0.05. Negative 1.3 and 0.05. So let's see where these two are meeting. And looks like it's going to be at 0.0885. 0.0885, right? So what you have to remember is you are not subtracting the z values. You are finding the area for each of these z values, and then you are subtracting that area. So this answer is coming out to be approximately 0.8589, or about 85.89%. So we are saying this total area is going to be approximately 85.89%. Okay, so I hope you can kind of see how each of these three different types of examples work out to be when we are asked to find the area, or like I said, as the probability, either to the left of the z-score, to the right of the z-score, or in between two z-scores. Okay, all right, now we are getting into our discussion for the probability distribution using the normal distribution. Okay, so they are basically saying, again, remember that normal distribution is a continuous distribution. So basically what we need to remember is that there will be no gaps in our curve. So for every z value on the x-axis, you will be able to find a corresponding height or frequency for that z value. So you will be able to find something that goes along with that z value on the x-axis. Okay. So again, that area under our standard normal distribution curve, you can also think of that as being a probability, or as the proportion of the population, for whatever example or characteristic we were looking at. So they're saying if it were possible to select a z value at random, the probability that we would choose one between 0 or 2 would be the same thing if you look at what the area under the curve would be between 0 and 2. So what you would basically end up doing is taking the 0 as your z value, finding its probability in the table, and taking the z-score of 2 and finding its probability or area using the table. You would subtract the 2, and that area would actually come out to be 0.4772. So we're saying the probability that we would select the z-score between the values of 0 and 2 is going to be 0.4772, or as a percent, you could say 47.72%. Okay? So since we are talking about probabilities, of course, we are going to use this notation right here. So if we're talking about finding a z value between 0 and, let's say, 2.32, this is how you would write it down, the probability of z less than, well, in this case, we're saying greater than 0, but less than 2.32. Now, normally we do not write it as this notation here, where you have less than equal to. We normally just use the less than symbol over here. And the reason we say we don't use less than equal to is because when you think about finding the probability for an exact z value, it's going to be 0, because your area is just going to be a vertical line. So if I wanted to know what's the probability that my z-score is going to be 1, okay, so think about this. If this is our normal distribution curve, in the middle is our mu, which is at 0. So if I wanted to know what's the area at this vertical line, which is going to be at 1, well, area of a straight line is just going to be 0, because you don't have any width in that, right? It's just a thin vertical line. And so it wouldn't really make sense to talk about the area at a given particular number. But when we talk about the area between two numbers, it makes more sense. So that's why we normally don't write it as probability of A less than equal to Z less than equal to B. We just write it of probability of A less than Z less than B. Okay? Alright, so let's look at this example here again and just make sure you guys are comfortable using the table and then thinking of this as a probability also. So this one, first one is asking us to find what's the probability that the Z value we select is going to be between 0 and 2.53. So if you go to 0, you actually have 0 right here, which is negative 0.0, and of course this is also 0.00 over here. So you can look at it here as being 0.500, or if you want to look at it on the positive side, you have 0.0, 0.00 here, and it is still going to be 0.500, which is basically 50%, right? So your probability for 0 is going to be 0.5, and then for 2.53, okay, so we've got 2.5 over here. We need to go to 0.03 here, so this is going to be at 9943, 0.9943 over here. So for 2.43, we are at 9943. Subtract these two probabilities, and you will have, as an area for the shaded part, you can think of it as being 4943 in your decimals, or 49.43%. So this can be area, but it can also be probability. Okay? For part B, they are asking us to find the probability that our z-score will be less than 1.73. So of course the first thing you want to do is go ahead and draw your curve, shade your area. So this is kind of what our diagram would end up looking like. And then let's go to the table and find our probability or area for less than 1.73. So then we need to go find 1.7. We need to find 0.3. So 1.73 looks like it's going to be this value here, 0.9582. So we go to 1.73 is 0.9582. So again, all of this shaded part is going to be 0.9582 or 95.82%. So again, think of it as an area, but you can also think of it as a probability. Okay, and then the last one was asking of finding the probability that our z-score will be larger or greater than 1.98. So again, draw your normal distribution curve first, shade your area, and now we want to know what that area or that probability is going to be. So for 1.98, we go for 1.9 here, 0.8 in that second to last column. So it looks like it's actually going to be at 0.9761. Okay, so 0.9761 for a z-score of 1.98. But remember guys, this is to the right of our z-score. So since it's to the right, remember we need to subtract this from 1. So you get 1 minus 0.9761, which actually gives you a very small probability of 0.0239, or basically 2.39%. So as a probability or an area, you're looking at 2.39%, right? So just again, it's the same process whether you're finding the area under the curve or you're finding the probability that your z-score will be larger than, smaller than, or maybe even in between two given values. You're still using the same process that you basically looked at in these first three examples that we did here, or you can always fall back to this little procedure table here to help you out. Okay? Alright, so they're saying sometimes one must find a specific z-value for a given area under our standard normal distribution curve. So that means they're actually going to give you the area, and we have to work backwards to find our z-score, which means you would go back to the table and try to come up with an approximate value for your z-score. Okay, so let's take a look at this example over here. So in this example, we are told find the z-value such that the area between the curve, the area under our standard normal distribution curve will be between 0 and the z-value of, well, actually we don't know the z-value, we know the area because the area is 0.2123. So they're asking us to basically find what that z-score should be. So basically we know that if this z-score is going to be to the right of our mean, which is at 0, and we know this little area is going to be 0.2123. So what you actually have to do, because remember our table always gives us the value which is to the left of our z-score, we actually have to add both these areas together. Now since this portion here, and let me show you, let's get rid of this guy here. So this portion here that I have shaded in blue, all of this is below the 0 z-score or below the mean, which means this half is going to be 50% or 0.5000. So we're going to go ahead and add our 0.2123 with that. So you take your 0.5000 and add the area which is given to us, 0.2123. So of course that will come out to be 0.7123. So when you go to your table, you actually have to look at this cumulative area of 7123 and see in our table if we can find that exact number. So of course, as you can see in this figure over here, we can find 7123 in our table, which corresponds to 0.5 and 0.06 here, which means you are looking at a z-score of 0.56. So that's going to be the z-score of 0.56. So let's go to our table and verify that. Okay, so for 0.5 here and then 0.06 there, we should be at 0.7123, and of course you'll notice that does work. So of course that gives us our z-score of 0.56. So this was just kind of an example to show you if you are given the area and you need to find the z-score, we can work backwards. But you know, sometimes what's going to happen is you will not be able to find that exact area. So you have to go for the closest value. So let's say they are saying we wanted to find the z-score for an area of 0.9241. Okay, so 0.9241. So let's see if we can. Okay, so 0.9241 is going to fall between these two z-values right here. So I've got 0.9236, 0.9251. So if we're talking about 0. And I'm just going to write it here, 0.9241, you can see 0.9241 is going to be closer to 0.9236 because it is only 5 units away from 0.9236. But if you look at the other value, which is 0.9251 over here, that's 10 units away from 9241. So of course our closer value is going to be 0.9236, which means we use its z-value, which was going to be 1.4 over here, and 1.4 and 0.03 over here. So this will be, our closest value is 9236, which corresponds to the z-value of 1.43. So if you don't find the exact value like we did here in this example over here, then you have to go for the closest area, which in this case for 0.9241 was going to be 0.9236, which corresponds to 1.43. So what they're talking about here in this example, and I'm actually going to leave it for you guys to read through this, is they're just basically talking about how is it possible for us to find the area and its corresponding z-score based on this idea of a continuous curve. So they're actually talking about, what if you were looking at a clock over here or a watch, and if the battery was going to go dead and you had to find the probability of where your minute hand would stop. So they're kind of using that example over here, expanding it to this rectangular space over here, of course giving you that same area of 1, like we're talking about our normal distribution curve here. So I would definitely encourage you guys to look through this little example of just this explanation here of how they're talking about how it is possible for us to find the area under our curve based on this. I think this is really neat. I think you would enjoy going through this. So just kind of read through it, because just me going over it is not going to make much sense. Because, of course, if you read it yourself, it will be more useful to you. But anyway, this is what we are looking at in section 6.1. Now let's go ahead and do some examples from our textbook so you guys can get a little bit more feel of how do we use our normal distribution table, and then of course get a little bit more comfortable with the normal distribution itself. Okay, so let's take a look at our first example here. It's actually going to be number 20. So they're basically saying find the area under the standard normal distribution curve. So we're actually looking at number 20 over here, which is asking us to find the area between the z-scores of 0.24 and z-score of negative 1.12. So let's take a look at this example over here. So it's going to be the area between z-score of 0.24 and z-score of negative 1.12. Okay, so if we draw our little standard normal distribution curve, something like that, okay, we know our mean is going to be in the middle, right, at 0. So we're saying this is going to be between the z-score of 0.24. Remember, z-score is basically your standard deviation, and then on the negative side at negative 1.12. So they're basically asking us to find this area right here in between these two z-scores, right? So we need to find each individual area first. Okay, so let's start with the positive one for z equals 0.24. And then we'll of course also find it for negative 1.12. So let's start with 0.24. So we'll need to go to our table over here, 0.2 and 4. So it looks like this will be meeting at 0.5948 from our table. Okay, and then now let's do negative 1.12. So negative 1.1 is here, 0.2 is here, so that's going to be negative 1.12 is going to be at 0.1314. Okay, so once you find your two z-scores, then of course remember, since this is in between, to find our final answer, we are going to be doing 0.5948, and from that we will be subtracting 0.1314. So if you put this in your calculator, you should get an answer of 0.4634. So this is going to be the area between these two z-scores. Now, of course, this example is talking in terms of area, but even if they were asking you probability, you would still be doing the same calculation. Okay, so this was number 20. Now, let's look at our next example. I wanted to look at one more over here, and we're going to be doing number 26 here. So they want to know what is the area, the total area, which will be to the left of the z-score of negative 2.15 and to the right of 1.62. So let's go ahead and take a look at this guy over here. So this is going to be the area to the left of z equals negative 2.15 and to the right of the z-score of 1.62. So again, we want to draw our normal curve first. Okay. Not a great curve, but you get the idea. So again, 0 is where our mean would be. And then to the left, we are looking at negative 2.15, and to the right, we are looking at 1.62. Okay, so they want to know the total area, which will be to the left. So this little part here of negative 2.15, and then to the right of 1.62. Okay. Now, let's see what each of these calculations would look like. So since we are doing to the left of negative 2.15, we will just look at the table directly and get that answer. But when we do it for the right of 1.62, remember we'll have to do 1 minus that area so we can get that little tail portion, which is going to be to the right of 1.62. So let's start with negative 2.15. So negative 2.1, and then we're going all the way to 5. So that's going to be this number over here, 0.0158. Okay, so 0.0158 for this guy. Now let's see what's 1.62 going to be. So 1.6, and then we go out to 2. We've already actually marked this from a previous example, which was at 0.9474. But then to find this area, we will actually have to do 1 minus 0.9474, which that answer, once we put it in, will come out to be 0.0526. Okay, so this area we are saying is 0.0526. This area we are saying is 0.0158. So of course they want us to know the total area, which means we add these two numbers. So you will get 0.0158 plus 0.0526, and that answer will come out to be 0.0684. And this will be our total area, which is to the left of z equals negative 2.15 and to the right of z-score of 1.62. Okay, so just two different examples to kind of show you how we can do these calculations. Now, the next example I wanted us to look at is going to be example number 48 over here. Okay, right here. So 48 is talking about finding the z-value to the right of the mean. So we're finding the z-value to the right of the mean for these given conditions here. Okay, so for the first one, they are saying find the z-value to the right of the mean so that 54.78% of the area under the curve will be to the left of it. For part B, it's 69.85% of the area will lie to the left of that z-score we're trying to find. And then part C is going to be 88.10% of the area is going to lie to the left of the z-score. So let's go ahead and take a look at this guy over here. So this is number 48, and they're asking us to find the z-score or the z-value. Okay, so part A, they're giving us 54.78%, which will of course be 0.5478. So what they are basically saying, if this is our normal distribution, right, mean in the middle, you are finding the z-score which is going to be to the right of the mean such that the area that lies to the left of this z-value, so all of this here, all the way till the tail, all of this area is going to be 54.78%, or basically 0.5478. So what we have to do is we have to go into our table, and in the table itself you have to look for 0.5478. Okay, so if you look at this table over here, on the negative side, our data values or our area or probability values only go to 0.4641, and again we're looking for 0.5478, which means we have to go to the positive side and then start looking till you find either a value 0.5478 or something close enough to 0.5478. And if you actually look right here, we have the exact value of 0.5478 right over here, which corresponds to 0.1 and then 0.02. So you're actually looking at a z-score for this guy as 0.12 when you put it all together. So again, if you go back to the table, I've got 0.1 from here, 0.02 from there for the 0.5478. So that's going to be our z-score. So you are actually able to find the exact value of z-score. So this guy is going to be 0.12. Okay, now for part B, they were asking us for 69.85%. So of course that's going to be 0.6985. Again, if we do a quick curve, oops, I'm really not good at drawing these, am I? Okay, so I'm new here, and now we're looking for a z-score where this area, again, all of it to the left, is going to be, this total area is going to be 0.6985, or your 69.85%, right? Okay, so let's go ahead and see if we can find a z-score that matches to 0.6985 in our table. So 0.6985, which will again be on the positive side. So let's go 0.69, okay, there we go, 6915, 6950, 6985. So it looks like we again found the exact value for 0.6985, and that is corresponding to 0.52 is what it looks like, 0.52. Okay, so again we found an exact area for our 6985, so that's a z-score of 0.52. 5, 2. Alright, so far so good. Now let's see what they're asking us for part C. And part C is 88.10%. Okay, so 88.10%, which again as a decimal will be 0.8810. So again, our little normal distribution curve. Okay, mu in the middle. And we're looking for a z-score, which will give us the area right here, all of this, which is going to be 0.8810 or 88.10%, right? So again, we want to see, do we get a z-score or do we have to find something close enough to that? So we're looking for 0.8810. So let's see, 0.88, okay. So we've got 86, 87, alrighty. Looks like we again are able to find the exact value of 0.8810 right over here. So that corresponds to 1.18 is what it looks like. So 1.18 is what we're looking at. Okay, so again we found the exact value, 1.18. So this was just to show you how the reverse examples work if they're giving you the area and then asking you to find the z-score that would go along with it. Okay? So I hope these examples were at least able to help you get a little bit comfortable with how to use your normal distribution table. And then we'll look at a few more examples when we are in class, but look through this video, look through your handout, and let me know if you guys have any questions. Okay? Alright guys, have a wonderful day. Be careful, stay safe, and I will see you in class. Take care. Bye-bye.